Okay, please take a seat. We will soon start the session on how to monitor the ocean with models. I think we are starting right now, so welcome to the Digital Ocean Pavilion. So after several sessions since yesterday on how to monitor the ocean, we started with how to monitor the ocean using in situ observations. And then this morning we learned how to monitor the ocean using satellite data from space. And now we are going to talk about models. So I am Marie Drevillon, working at Mercator Ocean International, and I will co-chair this session with my colleague Andrew Saulter, who is an oceanographer from the Met Office. I will first introduce this Slido poll. It's not really a poll, it's a question. Well, it's a website that you can access easily using this QR code, and you can ask your questions there online. In the room, don't hesitate when we have finished our talks to ask us directly your questions, of course. But without further delay, we'll start this session on how to monitor and forecast the ocean with models, and starting with my colleague, Andrew Saulter.
Thank you, Marie, and welcome everyone to this session on monitoring and forecasting with models. I'm Andy Saulter. I'm from the Met Office in the UK. We are the UK's National Weather and Climate Service, and we do marine weather as much as we do atmospheric weather. So why should we be monitoring and forecasting the ocean? Well, actually, we've always needed to understand how the ocean works. From ancient times going forward, we've needed to understand safe transit in the ocean. We've needed to be able to find food. We've needed to be able to understand when the tide's coming in and out of bays. And we still actually have all those same problems to deal with now. Fishing, safe transit at sea, safe transit of cargo. But we must also ask other questions. So for example, how do we use the ocean sustainably? How do we prevent or mitigate pollution in the ocean? And actually, what does climate change mean for the ocean's behaviours, and therefore our own well-being as we respond to those changes? And monitoring and forecasting is designed to help us get the evidence together that's needed to make decisions, and good decisions, about these things. So why model this? Well, models really are there to extend all the good information we get from observations. And observations are the lifeblood of what we do, and they're an incredibly valuable resource, but they actually really only scratch the surface of the ocean, sometimes literally. So satellite information, for example, really only gives us a picture of the ocean surface. This image here shows a picture of the Argo float array. There's about 3,000 floats in this picture, and those dots are not to scale because an Argo float is about the same size as I am. So it's not sampling great big portions of the ocean like that. However, when we apply that information into a model, we can extend its coverage and its value. So this is an example of a correction to a model data set that's made once we've applied something called data assimilation with these Argo floats. And we can see now that that information has been extended over a much broader area, and is now covering significantly more of the ocean's surface or subsurface than we'd have had with the observations on its own. And we can then turn those corrections to our model into an actual description of the status of the ocean, so something that we would call a gridded analysis, and that tells us how the ocean is looking right now. And then we can also project that forward in time and get a forecast, so understanding how the ocean's going to change in 4 or 5 days' time and even further forward. And so what modeling's bringing us is that ability to create a homogeneous data set, a gridded data set that's really easy to work with and interoperable, and can be put into systems for decision making, so for example digital twins, that allow us to then play with the information and understand how the ocean changes or how our changes to the ocean will affect things and decisions that we make. So how do we actually do the modeling? So here's some basic concepts. We divide the ocean into blocks, and each of those blocks has a set of process rules. The blocks are influenced then by a whole load of inputs. So for example, for growing waves, we might look at wind, currents, and sea ice as potential constraints. As the information changes in the model, it will talk to other grid cells right next door, and we'll basically expand and then create this overall coverage, a kind of sort of Lego world, if you will, that we can use to actually understand things. And from that basics, we can then build in a whole load of complexity. And the sort of complexity that we'll look at as modelers will be things like resolution. So for example, on the top left here, we increase the resolution of a surface current model that allows us to get a much better picture of the circulation and all the fine structures compared to if we just do it with a fairly basic setup. We can also get models to talk to each other, something that we call coupling. And that's really about trying to make a much better representation of the whole natural Earth system. The ocean does not operate in isolation to the atmosphere. The atmosphere does not operate in isolation to the ocean. And marine biology does not, again, operate in isolation to the ocean physics. All these things need to talk to each other forwards and backwards. And the more we can get those exchanges happening in a sort of a near real-time context in the models, the better a prediction we can actually make. And then the final thing that we try to do is to actually work out what uncertainty looks like for our systems. So no model is going to be a perfect representation of nature. That's not possible. But what we can do is we can try and understand what the error bars look like. We can try and understand where the model may or may not be completely right, and we can then use those bits of additional uncertainty to help us judge what we're doing with our decisions, to hedge our bets if we must, or to work with the biggest probabilities if we can do. Now, when we do all of these things, when you build complexity, you have to increase the amount of compute power that you use. Modeling is a compute-intensive process, and that means that we spend as much time working on the optimization and the IT skills that are involved with this as we do with the actual science. So it's a kind of cross-domain working environment we have that brings together software engineers as well as scientists to actually produce all this stuff. So what challenges do we have? Well, the big challenges we have are one about sustaining the mix of observations and models that we can have. Observations are absolutely the lifeblood of what we do. Without good observations, you cannot build good models. But models can be also really useful for observations in terms of understanding where and how to deploy things, optimizing the networks of observations you use. And if we have a good join between the two things, it really helps us understand the investment that we have to make in marine monitoring and observations offshore. We need to communicate uncertainty in useful ways. I suspect everyone's come across a weather forecast that's not been right. Quite often, those weather forecasts have been very uncertain, and that uncertainty has not been communicated in the way that it needed to be to understand where the error bars actually sat, and therefore why it may not be correct what the first judgment is. And trying to work out how to communicate that uncertainty is really important for everything that we do. We do need to extend what we can skillfully provide as ocean modelers. So oceanography is still a relatively young science, particularly compared to some of the atmospheric sciences. And so we're trying to model and predict things, so for example, biogeochemistry, movements of fish and stuff like that, that are really quite difficult, and we're still learning how to do that in the best way. So trying to get to ourselves to the point where we're fully meeting all of society's demands for decisions on the basis of what we do is still work in progress, and we're working really hard at it. And what we also want to be doing is working with new technologies and tools. So particularly the AI revolution is something we see as really powerful for improving what can be done with modeling, particularly in harmony between process models and these sort of statistical AI-based schemes. And you'll hear some talks on this a little bit later. So finally, I just wanted to finish for people who are looking at this and aren't necessarily from the world that I presently inhabit, as to who we kind of want to work with and who would be really useful to join the journey with us. So the first thing is actually users. So people who work with forecasts, with information, policy makers, helping us to actually understand what the critical things that we produce are, is always a really important dialogue for us and something that we would encourage. We really need to work with communicators that are very good at turning data, numbers into visualizations, into statements, into things that can be well picked up and used by users and policymakers who won't necessarily have the time or the inclination to understand all the nuances of the things that are done with the science. We need software engineers to work with us. As I said, it's really critical that we get software working really well to be able to do what we do. And of course, we need a new generation of scientists coming through, and actually scientists with both a passion for the ocean, but actually also a passion for people and for problem solving, because actually that's what we're really trying to do, is we're trying to solve problems to support the ocean and also support societies. So I will leave it there. Thank you very, very much for listening.
Thank you. Thank you very much, Andy. That was an excellent introduction.